Okay, let's start our seminar. So it is the third seminar. It will be about exponential family and conjugate priors. First, let's remind the previous lectures. We discussed how to construct the model. So we have some data and we want to find some density to describe it. From data, we can construct the features with the mapping, and we can find some important statistics. For example, the mean. And we discussed that to find such a density, we should maximize the entropy given this constraint about the statistics. And we solved this optimization problem and obtained that the solution has the following form. Okay, so let's discuss.
So sorry, can I ask? So I think we didn't have this on the lecture, so it's not a recap, it's something new.
We did this on first seminar.
So I missed because I registered later. Okay, sorry.
Yeah, this is recap of first seminar.
Okay.
Okay, and also there was an exponential family that described as if our density has the following decomposition. So we have our features, we have our natural parameters, we have normalization constant, and some additional function of data. Here we have that our phi-x is the minimal sufficient statistics. It is will be important for us. And also, what is important for us now that the functions of parameters and data are decomposed, and the only interaction between them is a linear function. So, okay, this is what the exponential family is. And on the second seminar, we discussed the regression or relevance vector machine for regression tasks. There we also have some data, some parameters, and targets. And we consider the following model as Gaussian distribution with following parameters. Sorry. Okay. And since our data is independent, the likelihood has the following form. And we choose the following prior. We choose the following prior with zero mean and diagonal covariance. And we fit our data with such model. To find our posterior parameters, we just explicitly solved these equations because with normal distribution, we can do so. So, and we obtain that is again the normal, that the posterior distribution is again normal with some parameters updated. And also, since we worked with convenient distribution, we found the predictive distribution here. But it is just a recap of second seminar. What was important that our likelihood was normal and our prior was normal. And with these assumptions, we obtained the closed form equation. So when it works in a general case, for this, we will use conjugate priors, and now we will discuss this. So first of all, let's try to solve following problem. Again, we have definition of exponential family, and please try to prove that our popular distributions such normal and multinomial are the members of exponential family. So you should take the densities or probability and show that there will be such factorization. And please notice that for multinomial distribution, we have this constraint, and we should use the minimal sufficient statistics. It will be important for you when you construct the representation. So please try it. You have 5-10 minutes. It is not hard, and we will discuss this. And of course, I speak sometimes fast, and don't hesitate to interrupt me, ask questions. I will try to answer all of this. Okay, so please try. Okay, let's discuss solution. Let's start from the normal distribution. For normal distribution, we just make explicit derivation. So we just expand our terms inside the exponential function, and we just add here our normalizing constant, and we just form it to make our decomposition form. So here we have not this our one term of phi and the second, and the same for parameters here, and we see that the inner product now can be written with these functions, not functions but terms, and also the part of normalizing constant and the part of exponential are from new normalizing constant a of lambda with all of this. Okay, there is no k of x, and here we can just we can make some additional substitution to achieve more convenient form, but it is not important. Our task was to show that it is the exponential family. So here it is. The next is...
sorry about this normal distribution. Should we also find this phi of x so that it is minimal or not?
Here, for normal distribution, it is known that it is minimal, since it is for mean and covariance. So we know this from course of statistics.
Yeah, but for this x transpose that is symmetric, and therefore if we have this lambda which has some 1 and -1 of the elements ij and ji, this will always give 0 with this scalar product phi of x, and with this specific lambda will be 0 because of this symmetricity of x transposed. So we should have not like m squared if we what is the dimension is d, not d squared of these elements corresponding to covariance, but the smaller number, so we do not include this symmetric part.
Maybe you're right, yeah, but no, but
this minimal property, is it really important? So I just it's new for me. I don't know why we really need this minimal property.
So let me think. I can't remember now, but let me write you after the seminar. What's your name?
Maxim.
Okay, I will check it. Sorry.
Thank you.
Okay. A good question. Okay, for the multinomial distribution, here we use that it should be minimal, because here we know that this constraint, and we can't just use all of x's, because some of them can be written with respect to others. That's why we should extract one of them and make substitutions. So we just know that, let's say, the last x, it can be written in this way. So we do this, we expand it from here and make all substitution we need, and we achieve this form. Here we don't use the normal constant. We just here we just show that how we use minimality of sufficient statistic. And now we can see that here sufficient statistics is so, and it is the minimal because we use on data points, and we can see that lambda can be written in following way, and we can construct new normalizing constant with all additional terms and show that pi can be written in the more convenient way with lambdas. No, it is again some convenient substitution, but the main part is to show that we have here the factorization. Okay, so this we show that familiar distribution such normal and multinomial are the members, and let's go further. Here's a new problem. Suppose we have binomial likelihood, so in this form, and we suppose that our parameter has prior distribution as beta distribution. And why we choose such prior? Because we want some functional matching between likelihood and prior, because we understand that then the posterior distribution will be achieved more easily. Okay, the prior distribution is not unique. We also can use some mixture of beta distribution or something else. But here we just consider this case because it is simple, and we will achieve some property, some interesting properties, and then we'll try to generalize them. So now please try to find following things like maximum likelihood estimation for this likelihood. Try please to find posterior distribution with such prior, and the predictive distribution. So the predictive distribution, it is with some new points, and it can be written like this. So please try to solve it. You again have 10 minutes.
At tau 1 and tau 2, some fixed parameters?
Yeah, it is
parameters.
No, it is some fixed hyperparameters.
in this second task, expectation of what should we find?
Expectation of parameter theta with respect to posterior distribution.
Mm-hmm. And what is the mean of this beta distribution?
For beta with such parameters, the expectation is this.
Thank you.
So I think we can discuss now. Hope you succeeded to solve some of the problems. Yes, okay. Let's discuss. First, for maximum likelihood estimation, we just can find it explicitly. We want to maximize such function. We apply logarithm function and just write what we have. We compute the gradient and we achieve that the solution for this equation is follows. But we also need to check that it is a maximum, and we can remember that for exponential family, we have that this term, it is a convex function. We discussed this in the first seminar. And obviously, when we apply minus, we obtain the concave optimization problem. That's why the solution is the maximum. Okay. Next, we try to find the posterior distribution. We apply Bayes rule, and we see that it is proportional to likelihood multiply our prior. So we just substitute these densities, and what we have, we can see that we can combine the terms and obtain that it is theta sum of x's plus tau sub 1 minus 1 and 1 minus theta in the power of 1 minus n plus tau 2 minus 1. And we see that it is the beta distribution, and we just updated the parameters. So here are new tau 1, let's denote it as tau 1 prime, and here the new tau 2. Yes, okay, so we see that in this case, the parameters are just updated when we observe some data. Okay, so what's about the predictive distribution? And the interesting property when we compute the posterior estimation. So we compute the posterior estimation. Since it is beta distribution, we can just calculate it as the expected value of this distribution. So we just use the parameters and obtain the following form. And it is interesting that we can decompose this expected value in this form. And what we see that it is the expected value of parameter theta with respect to prior distribution. And this term, it is the maximum likelihood estimation. So we see that our maximum posterior, expectation, it is the convex combination of prior and maximum likelihood estimation. So it is very interesting property, and in the end of the seminar, we will try to prove it in more general case. And also here we can see that how we initially have such observation. If we have more data, then the posterior estimation is more close to maximum likelihood estimation. Here we see because these terms start to converge to 0, and this term starts to dominate. So here we see it, and it is how we understand it intuitively. Yes. And the last one is predictive distribution.
Before we go to predictive distribution, so in the task we also had to derive this maximum the mode of posterior distribution, right? Or
no, map, it is the maximum posterior distribution. It is this estimation.
So because I thought that we also need to calculate the maximum, so the mode of this posterior distribution.
No, this is.
And it is turned out to be different than the expectation. So we have, instead of tau 1, tau 2, they wrote tau 1 minus 1 and tau 2 minus 1. So it's not like in the Gaussian case when they're the same.
Yes. Okay, any other questions?
And so can you again please say about this terminology when we, so can we go back to the task? So
okay, I understand.
What does map exactly means? So is it means expectation with respect to posterior distribution?
Yes, it's my mistake. It's not map, it is just expectation.
And when what is map means exactly? I'm confused a little bit.
Map, yes, it is when we maximize our posterior.
So map is the mode of posterior distribution?
Yes. No, not mode, just maximum. It is different terms. Mode and maximum.
But mode is the maximum because mode is the most probable.
Okay, I understand. Yes, in this way, yes. Okay. Okay, yeah, you're right. Sorry. Yeah, we just need to find the just expectation. And for predictive distribution, we have following form, and we have such assumption that new data is independent conditionally on parameters. So we just, to solve it, we just substitute the knowledge we have. So we have our likelihood, and we have our posterior. Here we just used new parameters. And we see that, wait a minute. That this term just can be extracted from the integral, and under the integration, we again have the beta distribution. And the integral, it is just inversed, no, it is just normalization constant, not inversed, normalization. So here, the interesting property is that the predictive distribution, it is just the ratio of normalizing constant. Okay.
And how the last equality is obtained? So how we go from this normalizing constant to this ratio with n, xn tau? So in the last line,
This one? We have, we just use our substitutions first. We remember that we have Okay.
Yes.
So we can just rewrite with gamma functions. And here we have gamma.
So this gamma functions of a sum is the same, would be the same of tau1 prime plus tau2 prime is the same as without primes, and this the other two gamma functions will give us this
yes,
two factors. Okay.
Yes. But the main property is this is not just a final solution, but this ratio. Because if with our choice of prior, we can compute predictive distribution more easily. And that's why we need to choose such priors. And we will discuss this. What general forms of priors we should use.
And this property that we have the ratio of update normalization, posterior normalization is will be common for these conjugate distributions, or is it specific to this to our
Yes.
case with this beta.
Yes.
So the common.
What? The
So this is the common property. So
This is
but
the
we have the ratio.
or sum of priors,
Mhm.
not for any prior, but for some form of priors. So we will discuss it now.
Okay.
So what we have? We have first that posterior distribution have the same form as prior. That's called the conjugate distributions. And we see that with conjugate distribution, we have predictive distribution with explicit calculation. Okay, so how we should construct our prior to achieve such good properties? Here it is. First of all, we again choose the model, the likelihood for our model, like previously. It is exponential, such exponential. It is not likelihood, it is the density. And the likelihood, since data is independent, we can write as follows. And now we construct the prior in the same functional form. So we have again exponential, we again have inner product, but with parameters, and here we have features, but here we have hyperparameters for our prior. Here we have normalizing constant, and here we have normalizing constant with some coefficient. In most cases, n sub 0 is 1, but there are some distribution like binomial where it arise. And here we have also normalization constant for this distribution, which doesn't depends on lambda parameter. So we use this form because it will help us to achieve good properties. It is our choice to choose such prior. It is not the rule, but if we choose such prior, it will be convenient for us. So now we will prove that with such a general form, the properties will be held. So first of all, we know that posterior is proportional to likelihood multiple prior. And if we rewrite it here, we see that we just sum it linearly, and we see that the parameters are just updated. So we see that the parameters of the posterior is just updated parameters of the prior. It is first convenient property because it is, no, we use conjugate, we obtain conjugate priors. Okay. The next one, it is a task for you to solve that the posterior distribution with such choose will also be the proportional of updated normalization constant and posterior. Here, the normalization constant in such form, that's why it should be inversed. So here we have h posterior divided by h updated. It is just the note for you. So please try to prove it. And don't forget that we already showed that the posterior, it is just conjugate distribution with updated parameters. You can just note it with some primes. Okay, let's discuss the solution. It is difficult. Here we have it. So we have the posterior distribution. We know it forms, and we just use our knowledge. We know that the likelihood has following form, and posterior distribution has the following form, since we just updated the parameters. And here we again can just extract the posterior normalizing constant because it doesn't depend on lambda. And we see that under the integral, we again have same distribution, but with new parameters, or so-called updated parameters. Okay, so we see that here we just achieve inversed H with such parameters. And additionally, we can also substitute the posterior parameters with initial ones, because we know the updating rule. Okay, any questions here? If no, we go to the last problem. Here it is. Now we need to prove the property about convex combination. It's already written about convex combination. So what you should use here, some hints for you. First of all, I remember what is mu, what is mean. Mean is written on the first slide, and it is the expectation of phi of x with respect to the distribution. And also on the first seminar, there was discussed the main thing to prove this is that the gradient of normalization constant is also not this is also this expectation you to solve this problem is to find the gradient of prior distribution and think how you can use it to prove this problem. And here we have the expectation with respect to posterior distribution. So don't forget to update the parameters. When you find something for prior, you need to update the parameters because here we have posterior distribution.
Excuse me, but did you mean to write like mu from alpha and gradient A from, I mean, not from alpha, but from lambda, and gradient A from lambda is just the same expression, or I don't understand something. I mean, like 1 and 2 in the right side, we have the same expression?
Yes.
Okay.
So I'm also confused.
From first seminar, you prove it is.
Okay. Must have forgotten.
So can you please repeat what exactly should we do?
Calculate this expectation.
And this is expectation. So mu of lambda. This is what?
Mu of lambda. It is the mean parameters. It can be expressed like this. You know that the gradient of normalizing constant can be expressed in the same way. So it is equivalently to find the following following expectation. And to find following expectation, you should use this hint. You can try in the different ways by, I think that it is the most convenient way.
Mhm.
Okay, I think we can discuss the solution. There is no solution in Czech format, so I will write it here and share the slides with notes after the seminar. Okay, the main idea is use this first and second steps. And what about third? We can calculate the gradient of prior distribution. And we see that if we will calculate the gradient, it is, since it is exponential function and this function doesn't depend on lambda, we achieve again the prior distribution. And since it is a complex function, we multiply it by tau minus n sub 0, the gradient of A. Okay, and what should we do next? Let's think, if we integrate this gradient, what we have? Since our density, it is very nice function, we can just extract the gradient out of integral. And what we have here, we have that just integrate the density, so it is a gradient of 1. So it is 0 for any value of lambda.
Oh, so, but we integrate over lambda.
Yeah, of course.
And take gradient also with respect to over lambda.
Yes. No. Yeah.
Then we cannot take out gradient. We rather should do something like, I don't know. Substitute a cent point. So if the problem with ID was one-dimensional, then it would be something like probability at minus infinity, at plus infinity, which is usually 0. But so the result, yes, so the answer is that the integral should be 0, but probably we cannot just simply take gradient out because it is the integration variable.
No, we have this integration with here we can just take the gradient out because we have a good family of functions. For some function, we can do so.
No, if lambda would be a parameter, not an integration variable, then we of course could take gradient out.
I understand.
But
maybe
lambda is integration variable.
Yes, maybe it is my mistake, and let me think. Yeah, of course, here we yes, I think it is not such. Yeah, we integrate not with respect to the gradient is about lambda, yes, but we integrate not with respect to lambda, but yes, but to respect with another parameters, because here we have no, if we integrate here, okay. Okay, maybe my solution, no, it is not wrong.
What we wanted, so can you please like go one step back, and what we actually, so what's the plan? Why we calculate this integral?
Mm. No, we integrate with respect to lambda. And here we can do it. I can't remember why, but here we can do it. I think I need to check it, but it is so, I'm sure.
Yeah, I also think that the integral is 0 at the end. We just probably should do some different reasoning, but the integral should be 0.
Maybe this way, this step have some mistake, but I have I solved it previously, and everything okay. Okay, but in the end it is 0.
Yeah, yes.
Okay, I will check this moment, but the most important that it is 0 for any lambda. And if we substitute, we see that here we have such equation, and it should be 0 for all lambdas. And here it is equivalently that tau divided by n sub 0 is equal to estimation with respect to this density.
Mhm.
Okay, and here we have the prior distribution, and we should update our parameters to make the distribution posterior. So we just update it, and we have that here we have such new parameter, and here we have such parameters, and here we have this term with respect to posterior distribution. And our aim was to prove that the convex combination. We can decompose it and see that is tau divided by n sub 0. Here we have n, and here we have such term. Yeah, and we see that this is the estimation with respect to prior distribution, as we talked earlier, lambda with respect to lambda distribution. And here we have maximum likelihood estimation. And we see that it is a convex combination. So if it is alpha, this is 1 minus alpha. So we prove this. And okay, I will check this step. But you agree that it is 0. Okay. So is it clear for you, the solution?
Yes, more or less.
Nice.
Will you upload the video of this as well, so
Yes,
you can
video
go through it?
slides with notes will be updated.
Okay, thank you.
And okay, to finalize the seminar, what we learned, we want to feed our data with some model, some density, and maximize the entropy. That's why we choose the exponential family and the distribution of such forms. The second, we want to make the posterior distribution, the posterior estimation, and predictive probabilities in explicitly and convenient way. That's why we should use the prior of such form, and for such form we prove that we will obtain good properties. That's that was about the seminar. And yes, as we discussed, my mistake that here, yes, this expectation is not maximum a posteriori, because maximum a posteriori, yes, it is the mode. It is the maximum of density. So here I have the mistake because it should be -1 and -2 here. It is just because we discussed it. Okay, thank you for your attention. And the important thing is that the next lecture will be face-to-face. Don't forget it, please.
Okay, but should we bring laptops for the offline lecture, or we won't have any coding part of the seminar?
In the next seminar, I don't remember, but some seminars will be with notebooks.
And on average, what would be the seminars? It will be like the previous seminar with coding exercises, or like this seminar with theoretical exercises? What is?
I don't know about the next seminar because it will be prepared by another person, but yes, some of the seminars will be with solving problems, and some seminars will be with coding. So we will have both seminars. But if you prefer some of this more, please write about it. Okay.
Okay.
Okay. Thank you and goodbye.
Thank you.
Thank you. Goodbye.
Thank you. Goodbye.